Okay, thank you so much, everyone, and a very good day to all of you. So today I'll be mainly talking about some of the research that we have been pursuing in our group in the domain of neuromorphic computing, and hopefully give all of you a flavor of how we are trying to bridge the gap and perform an end-to-end co-design going all the way between the hardware, software, and neuroscience layers of the stack. So if we look at the motivation behind neuromorphic computing, we are all aware that AI has made significant progress over the past few years. And if you really look at the flop requirements for various AI workloads, in the pre-GPU computing era, the rate of increase was more or less following Moore's law, doubling every 24 months. But over here with the GPU computing phase, we do see that the flop requirement has doubled every 3.4 months. And if you really look at natural language processing, then it's doubling every 2 months. So almost a 12-fold increase than what we have for Moore's law. This is from the compute side. Even if you look at, for instance, on brain simulation side, where people are trying to simulate the brain on best possible supercomputers that we have to diagnose various brain diseases and so on, we do see that there are orders of magnitude difference in the energy requirements of these systems. So therefore, in neuromorphic computing, we are really trying to understand how the brain works, its computational units, the circuit organization, and trying to imbibe that into how we are designing our hardware and algorithms. If we really look at the core computational model for neuromorphic computing, a vast plethora of works is based on spiking neural networks, where the systems are temporal and event driven, which is a significant difference from what we have in our current deep learning systems today. And because of this event driven nature of computing and data communication, you are really able to get orders of magnitude power and energy benefits in comparison to standard deep learning systems. There are also opportunities that we have been exploring in the domain of bioplausible learning, local learning, and so on. So once again, if we try to dig deeper as to where the inefficiencies lie in terms of the algorithm layer of the stack, there is the need to look at resource-constrained intelligent edge systems. There is a need to look at reduced number of labeled data that you would need during the learning process. We need to design lifelong learning systems that do not undergo catastrophic forgetting whenever you're faced with new tasks. We need to be robust to adversarial attacks. We need to also give uncertainty matrix in various confidence critical applications like self-driving cars, for instance. So all of these algorithmic challenges are present, and therefore the key question is, can looking at how the brain does computation enable us to overcome various inefficiencies that we have on the algorithm side? Now, side by side, if we look at the hardware implementation perspective, the inefficiencies really stem from two perspectives. First of all, you have core computational units in your hardware, which are the CMOS transistors, and they are really on-off switches, and they do not inherently map to the computational primitives of various neuromorphic algorithms. If we look at, for instance, a neuron design, you will require a large number of adders and multipliers. If you're looking at synapse designs, then for every single bit, I really need 60 or an 80 SRAM cells. So with a 4-bit implementation, I'm easily looking around 24 to 32 CMOS transistors per chip. Now, recent developments in the field of post-CMOS technologies, there are multiple emerging technologies people are looking at. Specifically, our group looks at ferromagnetic and ferroelectric devices, where we have single device structures that can be operated at very low terminal voltages, and their intrinsic physics mimics various neural and synaptic functionalities. So for instance, you are seeing over here a magnetic tunnel junction device, which I'll delve a bit deeper later on in the slides, where the free layer or the magnetization of the nanomagnet can be stimulated in response to an incoming current pulse, and based on the timing of the pulse, the magnetization profile or the conductance of the device can have a behavior which is very similar to, for instance, a leaky integrate fire spiking neutron. And even if you look at the physical equation, which is Landau-Lifshitz-Gilbert-Swansky equation, you see, for instance, the magnetization can be mapped to the membrane potential of a spiking neuron. The input over here can be mapped to the incoming current and so on. There's also a leak term associated with the magnetization. Now, this is one side of the story. On the other hand, we have the problem of von Neumann bottleneck, where because these are hugely memory-dominated applications, there is a huge amount of energy wasted just in memory access and memory leakage. So in this plot, what we are seeing is different data sets for pattern recognition, where the complexity really increases from the left to the right. And for more complex data sets, we are going to have a larger memory requirement for the model, and therefore more amount of memory, greater than 50% in some cases, wasted in just memory access and memory leakage. Now, if we were to look at some of the devices that I was just talking about, which are non-volatile in nature, and we arrange them in a cross-array structure like this, by very simple application of Ohm's law and Kirchhoff's law, we are able to implement the dot product in these in-memory computing kernels, and therefore this helps us to really bridge some of the energy bottlenecks that we have due to the von Neumann architecture. So this is just to give you guys a premise of where the opportunities stand for neuromorphic computing and what specific solutions we are looking at. So with this, let me delve a bit deeper and provide some snapshots of some of the research activities we are doing. First, I'll discuss a bit on neuromorphic algorithms. So if we look at training spiking neural networks, these are systems which are very different from current deep learning systems. These are based on binary activations, temporal behavior, and so on. And therefore, a fundamental rethinking is needed in terms of how you do training of spiking nets. So under the broad umbrella of various popular methods for training spiking nets, I'm showing here STDP learning, but this can be deemed as a local learning mechanism. There are various other methods that people are also looking at, where the key idea is that biological synapses update their weights based on firing patterns of local neurons, and therefore can be trained these networks using such a local learning scheme. STDP learning, for instance, is unsupervised learning. The application domain of STDP learning is, for example, edge devices, where I will have limited label data, but it has been relatively difficult to scale the accuracy of these networks up to deeper networks. Another popular mechanism is trying to train these networks using backpropagation through time. And while there has been significant developments over the past few years on getting accuracies in large-scale data sets, it is still hugely memory intensive because you are temporally unrolling the network. So the computational overhead required to train these networks through BPDT is significant. You also need to explore surrogate gradient techniques, for instance, to train these networks because of discontinuous spiking activity. As a middle ground, people have been looking at conversion-based schemes also, where you train a standard deep net and you deploy it in the spiking mode for event-driven inference. You're, of course, limited there by various constraints that might be present during the conversion process. Now, really starting off on various training methods, our group has looked at, first of all, really showing proof of concept demonstrations of very deep SNNs on data sets of the complexity of ImageNet, trying to showcase potential advancements of binary spiking neural networks, for instance, where we have been able to show that binary SNNs can really yield accuracies which are comparable to full precision SNNs. And therefore, you can implement them in very much efficient in-memory computing kernels catered for binary neural networks, but it do not suffer the accuracy degradation, for instance, that BNNs experience on large-scale data sets. Now, as a thrust in our group, we have been looking at hybrid algorithms where we are trying to train SNNs getting insights from standard deep learning. So for instance, there has been some work on really looking at combining the best of both worlds. Because backpropagation through time is cumbersome, can we look at a hybrid scheme where we convert the ANN to an SNN and then we do some epochs of BPTT training? And the key reason why we would like to do that is you get enhanced accuracies or reduced latencies in this. But even if you do, let's say, 5-10 epochs of BPTT training, that itself is very much computationally expensive for data sets like ImageNet, for instance. So our motivation over here was, can we really think of a hybrid algorithm where we are trying to avoid BPTT, but instead use a gradient-free optimizer like a neuroevolutionary algorithm to optimize specific properties that we have in a spiking net. And in this particular work, we really focused on the thresholds of the neuron, because the latency, the spiking activity, all can be interpreted of how your threshold is with respect to the spiking activity. So in this particular work, we are really trying to have an optimization space, where we are trying to optimize the individual thresholds of various layers in tandem with a neuroevolutionary framework. And the goal is to minimize the latency and maximize the accuracy of these networks. And we did see, first of all, a few interesting insights. If you were to look at just choosing a specific percentile of the threshold that you're getting from the histogram in an ANN, this is typically used in conversion-based mechanisms. If you look at BPTT-based training schemes, we see that our method of just neuroevolutionary approach is giving you significantly lower latencies and enhanced accuracy. And if I were to compare with BPTT-based approaches, we are seeing almost 2.9x less memory and 42x less runtime, even for 5 time steps being used for SNN simulation. Interestingly enough, we didn't stop there. We tried to understand why the thresholds are getting optimized the way it does. So for instance, one key insight we observed was that if you were to look at a neural network, it's basically performing the function of projecting information onto deeper layers. And therefore, if you were to look at the principal components or the PCs for various layers of a deep VGG net, and we try to plot the principal components, and over here, the blue line is really representing the percentage change in the principal components. We can say that when we have a larger percentage change, that particular layer is more significant. And we observed that that particular trend matched very well with our optimized thresholds that we had in the neuroevolutionary framework. And that does make sense, because higher the threshold, more accurate is your particular layer. And therefore, what the optimizer is really trying to do, it's trying to make sure that more significant layers of your network are performing more accurate computation. And these are graphs just showing the improvements in latency or accuracy of the optimized framework with respect to conversion-based. Similarly, if you look at adversarial attacks and you're trying to optimize a threshold specific to that framework, we see that layers where your adversarial noise sensitivity, this metric is basically trying to measure the percentage change in your neural activations corresponding to an adversarial perturbation, which is this minus the original activations. So layers, as you are seeing over here, some of the deeper layers have higher adversarial noise sensitivity, and that corresponds to the neuron thresholds optimized pretty low. And that again makes sense, because lower your threshold, more will be your discrete states. And we know that more discretization you have in your neural activations, then higher will be the susceptibility to adversarial noise. So once again, this kind of made sense. So this framework also gives the tool to develop interpretable SNNs. And we are really able to avoid some of the bottlenecks that we have for BPTT-based training. So that's more on the supervised framework of things. Recently, we have also been looking at upscaling unsupervised resonance by leveraging spike timing dependent plasticity. Now, this work is motivated by a deep clustering work that came out of Facebook, where the key idea was randomly initialized convolutional layers. If you just use them, you can extract non-random features. It will give you an accuracy which is higher than random chance. And therefore, can we use that and pass it through a clustering framework to give you pseudo labels that you use for the backpropagation process of the original CNN. Now, the framework worked well in terms of unsupervised learning on large-scale data sets, but the impact of the clustering process itself was not well studied. So in this work, we have been exploring how this clustering method performs in terms of bioplausible STDP-based learning versus other conventional clustering methods like k-means, for instance. So this graph over here shows accuracy versus the number of epochs, where you are seeing that deep cluster is essentially the one where you're using k-means for the clustering process. We are seeing that on tiny ImageNet, we are getting pretty good accuracies, outperforming the one by deep cluster. This shows from an information theory standpoint, Fisher information that is retained in the network. We are seeing that deep STDP really performs much better than deep cluster. These are some of the filters that we see in some of the deeper layers showing high-level visual features. And comparing with other metrics like normalized mutual information, which essentially tries to measure the mutual information between consecutive assignments of the clustering process, we are also seeing that deep STDP performs much better. So these are some of the recent works and efforts in our group on really trying to scale up spiking networks, going beyond what we have today. Now, the efforts that I talked about right now are more near-term efforts, I would say. Whereas we do realize that spiking networks, if we try to look at the current state of the art, they are lagging behind in terms of current deep learning systems, where in the recent past, we have seen significant achievements in natural language processing. Even if you think about the domain of local learning, hardware people are really excited by the prospects it offers, but it's really not scalable yet to large scale tasks. So driven by that motivation, the lack of SNN performance in the domain of sequential tasks, trying to scale up local learning, we have been really trying to think of SNNs as dynamical systems. And the notion that neurons in our brain also collectively converge to a collective state to better predict the input data has been a popular hypothesis. So therefore, driven by that motivation, we have been looking at energy-based models and learning frameworks for really scaling up SNNs to NLP-based sequential learning tasks as an example. So I'll be talking about two efforts that we have done recently in our group. The first one being in the domain of equilibrium propagation, or EP. So if we look at backpropagation training of neural networks, it is known that backpropagation does not use the same computational circuit, for instance, during both the phases of training, and therefore it's considered to be biologically implausible. It is also non-local, and therefore there is the need to look at other methods of training. Equilibrium propagation is considered to be a bioplausible training approach, which uses the same circuit during both phases of training. It is also local in space and time. The method really works on state transition dynamics of the nature shown here, where the state of different layers of your network evolve over time based on a scalar primitive function phi, which is analogous to the energy function of the network, and you have theta to be the parameters of your network. X is your input. The network operates over two phases. You have first a free phase where the model converges over time to a steady state S star. And then you have a nudge phase where you are implicitly trying to locally perturb the weights to minimize the loss function L. And over time, this also settles down to an equilibrium state S star, let's say. And once both the phases are performed, then you have the weights of the network updated using this particular equation. Now, equilibrium propagation so far was mainly evaluated for static tasks. And what we really wanted to investigate is whether we can scale equilibrium propagation to sequential tasks. And a nice synergy that we observed was actually coming from recent developments in the field of modern Hopfield networks. So we all know about Hopfield networks where you have, let's say, stored patterns x1 to xn. And you are trying to have a state pattern epsilon, and let's say you are trying to retrieve the stored pattern. And recently, with modifications in your energy function, for instance, this log square exponential function, people have shown that you can really store an exponential number of continuous patterns. And given a particular state pattern, the converged state is given by this particular relationship. And this has nice resemblances to self-attention mechanism that we really see in transformers. And over here, Q is the query which represents the state pattern. The key K can be considered as the stored pattern, and dk is the encoding dimension. So modern Hopfield networks, by a single step convergence process, gives you encoding which is very similar to self-attention mechanism, and this is also an energy-based model. And therefore, the key idea was observing this similarity can be club modern Hopfield networks to provide an energy-based self-attention mechanism in networks trained using EP. So that framework is shown over here, where the model architecture converges over time. The input layer, the weights are represented as the projection layer, and for the layers where you do have Hopfield attention, you're essentially merging the state transition dynamics as the query Q, and you have the key K, and this converges over time to provide you the self-attention mechanism. And we are seeing over here also that these are for three specific weights. The gradient estimate by equilibrium propagation is giving you similar updates as a BPTT based setup would give you. And over here on the right, we are seeing the convergence of the scalar primitive function phi. So using such a framework, you can also extend your analysis to going from simple-minded architectures, let's say on sequential tasks like IMDb, where you are given movie reviews and you would like to classify whether it's a positive or a negative review, for instance. You are seeing that once the Hopfield attention module is applied, you get significant accuracy improvements, almost 9% on the IMDb dataset. For even other complex tasks like natural language inference, we see that, for instance, over here on the SNLI dataset, where you're essentially given a premise and a hypothesis, and you need to find out the relationship between the two, we see that it's very easy to implement cross attention in these architectures, where I will essentially have a self-attention mechanism as well as soft alignment of the hypothesis with the premise. And you kind of club all these factors in together to get the final output. So these are some of our results where we have compared the EP-based approaches with other LSTM or GRU architectures. The key takeaway is that it is performing at par or better than other networks trained using BPTT. However, the advantage over here is that you have local operations, so compatible with in-memory computing platforms for neuromorphic hardware. You do not suffer the non-differentiability problem that we have for BPTT because you're not calculating the gradients explicitly. You do have on-chip learning capability. However, there are challenges that we need to overcome. We need to scale it to even larger networks. Simulation time is slightly slower than BP-based methods, and this does require convergent RNNs where you have bidirectional symmetric architectures. Okay, so this is kind of one recent work in the domain of energy-based learning in spiking networks. Another work which we have explored is using implicit modeling. So implicit modeling is used in the field of deep equilibrium models, where people have been trying to use it for training, let's say, very deep ResNets, for instance. Now, over there, if you think of that setup for an infinitely deep residual network, spatially after some layers, let's say, your output will be equal to the layer input. And therefore, if you do have such a stable convergence to equilibrium spatially, you can think of the optimization process to implicitly optimize a function g theta, which is tending to 0. And it is possible to show that minimization of the loss function in this particular case is essentially dependent only on Z star, which is the final converged state of your network, that is the equilibrium state, and therefore you avoid usage of any intermediate states of Z. This has one crucial advantage, which is you are able to avoid the requirement of storing huge computational graphs that you would require for BPDT based training in SNS. And therefore, we really try to go after this approach for seeing whether we can use this technique in NLP tasks, because BPDT even in static data sets is a cumbersome process, and therefore you really need to fundamentally rethink SNN training when you are trying to scale it up for natural language processing tasks. So over here, this is a spiking BERT architecture where we have an encoder based setup. The encoder layer schematic is shown over here. You have attention, addition and norm operations, and spike generators after each layer. What we showed was that if you have such a network, it is possible to show that your average spiking rate, or the ASR, of both linear operators like addition, operation, and so on, as well as non-linear operators like attention, converge to an equilibrium state after a few time steps. I mean, essentially this graph where I'm plotting the mean ASR per layer. For various layers, I've plotted this. And over time, we do see that things converge over time. And if you do see such a convergence to an equilibrium state, it is possible to come up with fixed point equations of the form shown here. Z equals to F theta Z. And therefore, we are kind of using the implicit differentiation theorem. Instead of spatially, we are using it temporally over here. And we are able to avoid usage of all the intermediate states of the neuron activations for calculating the weight updates of this network. So this really enabled us to utilize a spiking language model without using BPTT, as well as use other novel techniques from ANN literature, like, for instance, knowledge distillation. So knowledge distillation therefore allows us to transfer information from a deeper ANN-based language model to a much shallower SNN-based language model. And what we are really using for the knowledge distillation process are the converged equilibrium states. For this specific spiking BERT architecture, we performed both general over Wikipedia and task-specific distillation. And these are some of the ablation studies over here, as you are seeing. This shows effect of normalization operation. The final accuracies remain unchanged, but with normalization, the convergence is much faster. These are for different encoder layers. So if we have 2 layers versus 4 layers, the accuracy, of course, improves. And you can kind of do energy and power trade-off. We know that if we increase the threshold in a spiking network, for instance, the spiking activity is reduced down at the cost of increased latency. So there is a nice opportunity to figure out an optimal energy efficiency factor based on the spiking thresholds and the time steps being used for convergence. So this is the first work to really implement a spiking language model to be evaluated on the GLUE benchmark for text classification and regression. And using the proposed knowledge distillation framework really enabled us to scale the accuracies by more than 5%. And we are really implementing this using a much shallower spiking BERT model. This compares also with various other works in literature, as well as various efficient implementations of the BERT model, for instance, tiny BERT and so on. And we are really performing better or at par with many of the other implementations that you've seen. Okay, so with that, I will change gears a little bit and try to discuss some of our works on the hardware spectrum. So as I mentioned, our group primarily focuses on ferromagnetic and ferroelectric devices, primarily from the perspective that the programming energies for these device technologies are much better in comparison to other competitive technologies like RRAMs and PCRAMs. And you do have decoupled write-read current paths, low programming time durations, on-off ratios, and so on. So first, let me talk a bit about magnetic tunnel junctions. A magnetic tunnel junction device is essentially one where you have two free layers of, you have two magnetic layers. One is the free layer and the other one is the pinned layer. And by appropriately passing current through the magnetic tunnel junction, I am able to program the device in either a parallel state or the anti-parallel state. Now, this is a bistable memory. You can potentially program multiple states in the device by envisioning a device structure where the free layer is a bit elongated to stabilize multiple magnetic domains. And therefore, by passing current through the device, I'm able to program multiple states in this domain wall-based magnetic tunnel junction. This showcases some of the key device properties. This also uses an additional emerging physical phenomena that that is pretty attractive for spintronic devices, where you have a heavy metal layer on the bottom. Through spin orbit coupling and spin orbit torque, you are able to transfer multiple units of spin angular momentum whenever a charge current passes through the heavy metal layer between terminals T2 and T3. And subsequently, you are able to read the device state through T1 and T3. So these are magnetometallic devices. The input resistance in the path of the right current is very low. The energy consumption is also very low, as you are seeing over here. The terminal voltage drop for neuron devices, which can be scaled down pretty much, can be of the order of few tens of millivolts. Now, of course, you can use this device as a synapse depending on the relative proportion of the parallel and anti-parallel domains that we have in the device. You can also use this as a neuron device, for instance, where I have a reference MTJ, and if I pass some current, I will program the resistance of this device, and therefore this gate voltage will change, programming the output current through this transistor. And once again, by simple modification of the device structure, where I have the pinned layer at one extreme edge, I am able to get a spiking neuron, where once the input spikes trigger the domain wall to reach the opposite edge, I will trigger an outgoing spike. So using this framework, one can think of in-memory computing kernels like the one I was showing previously, where you are seeing decoupled write and read access transistors over here. And I have the synaptic devices, and these output currents directly pass in as input to the spintronic device. Now, this is a crucial advantage because over here, the neurons are current driven, so they require input currents. As I mentioned, these are low resistance paths, so you can kind of maintain all the columns and virtual ground. And because these require very low currents for switching, you can drive all of these crossbar arrays at a few hundred millivolts, let's say. So the key advantage over here is you can disregard some of the costly analog to digital converters that end up consuming a huge amount of power and energy consumption in these in-memory computing arrays. Another advantage of this framework is that the neurons are non-volatile in nature. So in a SNN-based setup, you can avoid costly memory transactions associated with memory and potential state updates as well. Now, driven by the motivation that these devices, by very simple modification, can switch between ANN and SNN modes. We wanted to look at a hybrid ANN SNN design. And the key reason is when you really look at very deep SNNs, because your signal propagation has to take place through all the layers, the latency increases. And therefore, can we really operate the crucial layers of the network, which turns out to be the initial half of the network where the peak power consumption is very high, in the SNN mode, while the lesser power consuming layers is operated in the ANN mode. And we explored this hybrid ANN SNN design framework, and we observed that this could potentially reduce the energy consumption of such a hybrid ANN SNN spin system by almost 1.5 to 3x. And we evaluated this in terms of an architectural framework like this shown over here. And as you're seeing, the huge energy benefits that we are seeing in contrast to other works are primarily stemming from advantages at every layer of the design stack. For instance, on the devices, we are really able to operate them at low terminal voltages. The crossbar arrays you can operate at few hundred millivolts. You are able to get rid of analog to digital converters, though with the caveat that once the data needs to exit a particular tile, so a tile over here is composed of, let's say, 4 neighboring cross arrays. For the neighboring cross arrays, we do analog merging, whereas if the data needs to go out of the tile, we convert that to the digital format. So we are reducing to some extent A to B conversions. Considering all of these factors, we were really able to showcase significant improvements in comparison to other device technologies. Now, this is more on the inference side. On the on-chip learning side also, we have been looking at opportunities that various emerging device physics can enable. For instance, one particular example is voltage-controlled magnetic anisotropy, where by applying a particular voltage to your magnetic tunnel junction, you can reduce down the anisotropy barrier that you need to overcome for the switching process. And people have been able to demonstrate really low energy switching with VCMA as opposed to standard spin transfer torque based switching, STT-based switching. And you can do this with very low programming pulse durations, for instance. Now, can we use this for mitigating sneak path problems that we have? So, for instance, in order to solve sneak path issues, one often adopts the case where I have a programming scheme like this, where if I were to just apply a programming voltage, there is the possibility of unwanted sneak path currents flowing into neighboring cells. But if I were to look at a programming scheme like this, where I have half of the programming voltage applied to the non-used rows and columns, I do mitigate that problem, but I do have half selected cells over here where there is undesired and energy consumption present. So therefore, the question is, can we look at nonlinear device physics to mitigate that problem? Now, this was not looked at so much for the case of spin synapses. Now, when we try to look at MTJ, where the switching is dominated by VCMA, we see a switching profile like this, where the pulse is around 1.8 nanoseconds, but you see that there is a very sharp transition of the switching probability to high values. And this is the part where the switching is dominated by VCMA. And that really half of the switching voltage, it will be dominated by spin transfer torque, and therefore you will really have a very low switching probability. Beyond this, there is also some decrement of the switching probability because of some lack of robustness during the switching process. That is something we are not really using for this work. So if you look at using VCMA and let's say using an operating voltage of around 0.7 volts, what this plot is showing is that if I were to use it with a combined pulse of 0.6 volts after that, just to ramp up this programming probability to near about 100%, you can potentially achieve that very close for pulse durations of the range over here. In comparison, a singular STD pulse of the same duration is not able to give us that same probability. And the half selected cell is almost exhibiting no switching probabilities in itself. So what are the advantages for looking at BCMA? The advantage is that first of all, I have huge energy efficiency because for reasonable pulse widths, I have a good amount of switching probability. You also have a very good differentiation between half selected and selected cells because of this nonlinear transition. You're able to separate the two very well. This is in contrast, if I were to just use STT switching, I could potentially achieve that, but I really need to play with the pulse width there to achieve the scenario that, okay, at a particular pulsing voltage, I have 100%, and at half pulse amplitude, I have near about 0. So that design space exploration is very constrained in an STT-based framework. That's something we try to really show in this particular talk. Now, another technology, as I mentioned, that we have been looking at are ferroelectric field effect transistors. This is work that we are performing through a DOE FRC on 3D ferroelectric microelectronics. And the transistor shown over here at the TEM is basically from Global Foundries test devices that we have. And unlike prior works on looking at ferroelectric field effect transistors for synaptic learning, our goal has really been to go after the route of leveraging intrinsic nonlinearities that we have in the device for performing computing. So what I mean by that is these are characterization results obtained from the experimental devices. And as you see, the change in current or the synaptic plasticity as a function of the programming voltage does experience a nonlinear variation, first of all. And it is also dependent on the current state of the device. And therefore, the goal was, can we leverage that in some way? We found out that these huge nonlinearities that we see, along with the state dependence, can actually help us to reduce the training samples that we need for learning in an unsupervised learning framework. So this was really good in terms of reducing down the costly programming events. So from an energy consumption viewpoint, we are trying to reduce down the energy consumption to two routes: the intrinsic efficiency of the device, as well as the dynamics leading to algorithm benefits. And this is a cartoon showing a potential arrangement of the FFS in an in-memory computing setup. So to summarize our efforts on the hardware side, from the ferromagnetic device standpoint, we do device fabrication and characterization in our own lab, whereas for the ferroelectric devices, we are part of the center where primarily the experimental efforts are in collaboration with other groups, and we are looking at a host of device technologies for ferroelectric FETs. For instance, we are looking at multi-gate devices. We are also looking at potential opportunities by other device structures, for instance, ferroelectric capacitors, tunneling junctions, and so on. Now, given the fact that we have these analog states in these devices, what we often miss is that with scaling, you would potentially start losing some of those large number of states. However, it turns out that usually I will have enhanced stochasticity during the switching process. So this slide shows magnetization dynamics for a magnetic tunnel junction where I have a relatively higher barrier height over here, 10 kT for a neuronal device. And we see that corresponding to an input pulse, we have a switching probability of the nature shown here. However, when you scale these devices down to 2 kT or so, you observe telegraphic switching, where by passing a particular current magnitude, the average magnetization has a similar response. So people have been exploring telegraphic switching from the perspective of really fast transitions, low energy consumption, and so on. However, majority of the works have been really looking at it from the perspective of rate coding, in the sense I tap out the average magnetization from these devices. So our thought process was, are we missing out on the temporal switching patterns that we have in these devices? Now, in order to look at that, this slide kind of highlights what I was saying in the previous slide. In a magnetic tunnel junction where you do have this telegraphic switching, let's say I have no voltage applied to it. The parallel and anti-parallel device lifetimes that I have in these two states are almost equal in that particular state. So that corresponds to the 50% switching probability that we will have over here for zero current. Now, as you are increasing the input voltage, the two lifetimes start getting modulated together, they change together. However, your average magnetization kind of gives you that sigmoid probability distribution. Now, we know that in a magnetic tunnel junction, in addition to the spin torque, you do have a magnetic field. And the idea was, can we exploit both of these control knobs to independently control tau p and tau a? And what we would achieve as an after effect of that is a stochastic spiking neural network with temporal information encoding. So this shows a device proposal where the magnetic field effect, of course, you can have that by an external magnetic field. If you would like to avoid that because of localized field being difficult to achieve, you can achieve it through a magnetoelectric layer where this voltage input is able to have a effective magnetic field effect on the magnetization. So these graphs show over here the fact that with these two input voltages, V1 and V2 are the corresponding Vi and Pmu over here, the tau p and tau ap kind of varies as a function of one of the voltages. So therefore, can we think of a neural network where the P state is essentially the silent state and the AP state is essentially the spiking state of the device. And therefore, tau P is a function of V2 from the previous slide, and tau AP, we are keeping it fixed corresponding to a particular voltage. And we do see that over a particular voltage range, it is possible to modulate tau P, which becomes our activation function in temporal encoding, and this remains relatively constant. And we have been trying to leverage that for the purpose of SNN training. And as you see over here, this is a probabilistic method of training the network with tail divergence, where you're trying to make sure that you are training your device lifetime distribution, which is exponential in nature, close to your target device lifetimes. And with that, the end result is you can potentially achieve a significant amount of reduction in the spiking sparsity for these networks. So that was one particular example. We are also looking at stochastic switching in ferroelectric devices, and I'm going to skip that today for the lack of time. We are also expanding efforts on the experimental side to showcase prototype demonstrations for on-chip learning. For instance, in this particular work, we have been looking at some of the spin orbit torque devices that I talked about and trying to understand the interplay of device sizing with various effects like the probability switching window and what effects that can have at the system level. In particular, for instance, we have looked at hardware in the loop training setup, where this is, of course, on a prototype network with 4 neurons. We are in the works for scaling this setup up, where you are seeing that with different devices, you do have device-to-device variations. However, if you do a hardware in the loop training where the variabilities are in loop during the training process, you perform much better in comparison to a software-only training where the accuracies are pretty low. Now, trying to summarize my talk, I will try to outline our outlook on really bridging the gap with neuroscience and looking at it more both from a ground up as well as a bottom up perspective. So we believe that we need to look bottom up and investigate computational units of the brain that do contribute to cognition. And as a particular example in our group, we have been looking at astrocytes or microglia that constitutes a significant proportion of cells in our brain, potentially greater than 50%. It does have important role to play in cell repair, neuron activity modulation, and so on. However, its role in the domain of neuromorphic computing has been relatively understudied. So over here, as you are seeing, astrocytes really perform a global neuron activity regulation mechanism where it is sharing information across multiple neurons through 2 potential chemical pathways, which are referred to as DAC and ESP. And what really happens is if I have multiple neurons connected to an astrocyte, and if I, let's say, have faults in synapses occurring in a particular neuron, then the neuron activity will start to reduce. This is, for instance, shown over here, where these are transmission probabilities of various synapses, and let's say a fault occurs at 200 seconds, and you see that the firing rate reduced, but sensing that information, there is a chemical that is DSC that reduces down in magnitude. This is in the negative side, so it's reducing down in magnitude as faults takes place. However, ESP is a global signal that communicates the information, hey, this particular neuron's activity is reducing, but all the other neurons are still firing at a higher rate. So using those two factors, it tries to ramp up the transmission probabilities of healthy synapses so that the activity recovers to some extent. And the key idea was, can we use that self-repair mechanism for autonomous self-repair of neuromorphic hardware, where you can potentially have faults. In addition to simple-minded faults, you can have other non-identities, for instance, temporal decay, for instance. So we really tried to do a hardware-software co-design approach, and the main goal was to really look at developing a macro model for the astrocyte self-repair process that encapsulates the temporal dynamics. So over here, you are seeing this exponential behavior kind of modeled over here. And this is the transmission probability, which kind of maps to the synaptic weight that I would have in my cross arrays. And this is being expressed as a factor Q, which is called the self-repair ratio. By computational modeling, we are seeing that it's mapping to 1 over Z, where Z is the fault severity. It is basically the sum of weights after fault injection versus before fault injection. So using this framework, it's very simple to implement that in a local learning setup. And few key things I would like to stress over here is that you have a self-repair learning rule which is local to your neuron as well as your synapse, and it is modeling the temporal dynamics to a huge extent. So when compared with global learning rules that was explored in prior work, we do observe a significant improvement in accuracy as well as the time steps required for the convergence process. So that's one. Along with that, we are also looking at a top-down perspective. Can we look at neural architectures beyond conventional feed-forward architectures? For instance, in convolutional neural networks, we mainly have feed-forward projections, but in the brain, you have feed-forward as well as backward projections present. One potential architecture in deep learning that tries to address this is in Bayesian deep learning, where you are really updating the posterior distributions of the probability distributions in your neural network based on the prior information. So we have been looking at accelerating Bayesian deep learning hardware, for instance, where you can tap out the intrinsic switching probability. For instance, if I have a bunch of magnetic tunnel junctions, each giving me a true random number, and then by using central limit theorem, if I sum up all the random numbers together, I will end up getting a Gaussian probability distribution like this. And this can be orders of magnitude potentially energy efficient than a corresponding CMOS-based implementation. So with that, to really summarize my talk, our group is really trying to bridge the gap going all the way from devices and circuits to machine learning and computational neuroscience to really perform an end-to-end co-design across the computing stack. And a huge shout out to all my students and postdocs who have really performed all the hard work, and also acknowledgements to our funding agencies. This is where I would like to conclude, and I'm happy to answer any questions, and also a link to our GitHub page where we do have open source code implementations for a large number of the algorithms I talked about.